All right, today we're taking a look at section 3.4, which is graphs of polynomial functions. And much of what we've actually got to write down here in a minute, you've actually seen before. There's one piece definitely that we haven't, and I alluded to it last time where I said, you don't know which way the ends of the graph point, but I do. And now you will know how I know. So that's the new piece of information. So we're going to work in this section on graphing. And you're always welcome to confirm graphs with graphing calculators. I don't have a problem with that because I'm requiring that you justify what you're doing algebraically anyway, so it doesn't really help you if you don't know what you're doing algebraically. All right, so let's take a look. There are 5 keys to graphing. The first 3 we have additional slides on, so I'm not going to go into them in detail. The first one is to check for symmetry. We've actually talked about this. We'll talk about it again. The second one is to find zeros and multiplicities. We've talked about that recently, like in the last couple sections even. Determining end behavior, that's the new piece of information that we have not talked about at all yet. And the last 2 points are really more for your reference. Sometimes the first 3 are enough, and you can get a pretty good graph from that. But sometimes they're not. Sometimes you need to plot some additional points to see what's happening. And then the last one is that you should be aware that polynomials are always smooth. There are no sharp turns like absolute value graphs would have. They're always smooth. So when you are connecting points, they shouldn't be connected in a connect the dots kind of way from Chili's, kids menu. They shouldn't. They should be connected in a smooth curve. Anyone still writing? We're good? Okay, let's go through the first 3 in a bit more detail. The first one we have seen before, but it was in the last chapter. So just as a reference, symmetry. We have 2 types of symmetry, specifically y-axis symmetry. And an example of y-axis symmetry would be the graph of y equals x squared. If you flipped it around the y-axis or you reflected it over the y-axis, the graph wouldn't change. Okay, that's y-axis or y-axis symmetry or an even function. The second type of symmetry we looked at was origin symmetry. These were odd functions. An example of this graph would be y equals x cubed. And the image you want to have in your mind is that it's like the spinner on a game board. If you put the spinner's, brad, the rotating piece, at the origin and you spun it 180 degrees, it would land right back down on top of itself. That's origin symmetry. And we looked at it in a couple of ways, specifically. We looked at it at testing the particular value negative x. We plugged negative x into the equation, and we did it for both cases. It wasn't just for the even ones. We plugged in negative x, and the results came out to tell us which kind of graph we had, if it was one of these at all. So on the first one, if you plugged in negative x, you ended up getting the exact same function that you started with. And in particular, it's the signs that we're concerned about. The signs are what might potentially change. On the second one, when you plugged in negative x, you got all different signs. Like every single sign changed. So you got the opposite that you originally had in terms of positives or negatives. And you guys had a test question about this, right? Where you had to decide, is it even, odd, or neither? And of course, if it doesn't do one of these 2 things, it's neither. Okay, so that's symmetry. Symmetry can help us to graph our equations. There is an example, we won't get to it today, where determining, you'll see why, but you're determining whether it's even or odd is really more trouble than it's worth. Most of the time it's pretty straightforward, but there's an example I'm going to show you where we're going to kind of skip over it and you'll see why, and we'll come back to it later in the particular problem. All right, our second one is the one we've done most recently, the last section of material, in fact, in 3.3. It's talking about multiplicities. X-intercepts, places where you cross the x-axis, have certain kinds of behaviors. So if c is a root or a 0 of a polynomial with multiplicity k, Okay, so if k is odd, the graph cuts through the x-axis, and if k is even, it bounces off the x-axis. And I should have left some space, but I'll give you an example of these two. Just jot this down first. All right, we talked about multiplicities last time. You took a quiz, and it was mentioned in the quiz. How do you decide the multiplicity of a particular zero? What do you look at? The degree. The exponent, right? The exponent or the power or the degree that's on that particular factor. So if you had an odd exponent, so something like this, you had x minus 2 cubed, right? That exponent is a 3, it's odd. You cut through the x-axis at that particular x-intercept value, which would be x equal to 2 here. But if the degree, we'll use the same x-intercept, if the degree were even like an exponent 4, it would bounce off of the x-axis. So you ended up with a graph on this one looking something like this, and a graph on this one looking something like this. Do you remember me referencing and drawing some sketches like that a little bit last time? We didn't do really any graphing, but I referenced this. Okay, this is going to be useful for our information in this section in sketching these graphs, knowing whether we bounce off or cut through the x-axis. All right, ready for the third slide? This is the last slide of like content you're going to have to just write stuff down on, okay? I know, it's a lot of writing actually on this particular lesson, but this is the last slide. We have not talked about this before. This is called end behavior. Okay, the end behavior means what happens on the ends of the graph. Does it go up for infinity or does it go down to infinity, negative infinity? And it's always going to be one or the other for polynomials, okay? Always. So our question is simply, which one does it do? So write down what this slide says, and I'll stop talking, and then we'll chat about what this is telling you. Okay, so let's talk a little bit about what's going on with this information. I referenced last time that I might be a little bit OCD. It was on a problem I talked about where we were doing decreasing order of exponents. Do you guys remember what I'm talking about? And I said you don't have to do it that way, but a lot of people like to see the exponents go down as you're moving from left to right. Well, if you put them in that order, so the highest degree term is at the beginning, then the coefficient, that means the number in front of that term, is called the leading coefficient. So a leading coefficient is the number in front of the highest degree term, okay? So when it references the leading coefficient test, that's what it's talking about. So if f of x is your polynomial, you have a degree of n, and the coefficient in front of that largest degree term is what determines everything, okay? So the first thing you have to decide is your highest degree even or odd? That tells you which row you're on. And then is the coefficient in front negative or positive? And that puts you in a specific quadrant of this particular chart. So I'm going to draw kind of a picture of what this looks like. These are just looking at the end behaviors of the graph, okay? So I'm going to draw something in the middle of it, but that's not necessarily the case for all graphs. The first one talks about going down on the left and up on the right. So a graph that looks something like this would be an example of that. And again, remember, we're looking at the ends. It's down on the left, it's up on the right. And if you flip that around, you know, kind of like 180 degrees, basically, you would have down on the right and up on the left, and it would look something like this. Okay? Again, I may not have that loop-de-loop in the middle there, but that's the idea on the ends of the graph. Even graphs, or at least even in terms of the exponent itself, the highest degree, are going to look something like parabolas on the end. They either both point up or they both point down. They may have some bouncing around in the middle, or they may be flattened out like a parabola would be, but if you had up on the left and up on the right, it would look something like this, at least on the ends of the graph. And if you had down on the left and down on the right, it would something like this, at least again, on the ends of the graph. Okay? So this kind of gives us some kind of an idea, because you could be bouncing off from above the graph, or you could be bouncing off of the x-axis from the below the graph. And until now, you haven't actually known how you would bounce. Isn't that exciting? You didn't know how you would bounce. But I'm going to show you how you're going to bounce, okay? Let's do an example together. All right, this equation, we're basically going to go through those 5 steps to the keys to graphing that we had at the very beginning. And the first step was what? Symmetry. So we're going to look at whether or not this has any symmetry that can help us, basically. So step number 1 was about symmetry. And how do we test for symmetry? What did we say back on that slide for symmetry? We plug in a negative x. You got it. Good job, Molly. Okay, so we're going to put in f of negative x. Into each of the x locations, remember parentheses are key to making sure that we get them, evaluated properly. So it looks something like that. Starting at the left, what happens when you have negative x to the third? Does the negative stay or go? It will stay, right? Because I have 3 negatives I'm multiplying. Okay, just think inside the parentheses, just the negative x squared, right? This part of it. What would this part be? That would be positive, and then it's got another negative in front of it still, right? So it's also going to be a negative x squared. And then I have a negative or an opposite of negative x, so I get a positive x, and then plus 1. So in order to decide if it's y-axis symmetry or even, or origin symmetry or odd, we're looking at the signs. 3 options. Either all the signs stayed the same. Did that happen? No. All the signs changed. Did that happen? No. Or it's neither. And this one's neither, which kind of tells us basically that symmetry is of no use to us. There isn't any symmetry, at least not the standard symmetries we look at, to be helpful for us in graphing this function. So this one's neither. Our second step is to look to evaluate intercepts, x-intercepts, okay? So how do we find x-intercepts? Well, we did it with synthetic division last time, and that's totally fine. We can use synthetic division. But on this particular one, we could also use factoring, and that's probably a little bit more straightforward. Now, we've seen back in like chapter P, which was like months ago at this point, I think, how to factor 4 polynomial, like a polynomial with 4 terms. There's only one way we can do it if it even works. What is it? Grouping. So we're going to attempt to factor by grouping, and if that fails, then we would be, on to synthetic division as our next choice. But this one actually works to factor by grouping. So here's my groups, the first 2 and the last 2, if I can. What do the first 2 have in common? Yes, they have an x squared I can factor out. And if I factor out an x squared, what am I left with? Good, x minus 1. Now, the only way factoring by grouping is useful is if I get another x minus 1. And right now, I don't exactly have x minus 1. So what could I factor out of the negative x plus 1 to give me what I want? A negative 1, right. So I'm going to pull out a negative 1, and I'm going to end up getting then x minus 1. Is everybody good with that step? It has been a couple months since we've done that, so. Okay, fabulous. So the whole goal was that these pieces matched, and if indeed they do, then I can factor them out in front. So what does that leave me with that's not underlined? Right, x squared minus 1. And can that be factored further? Yes, it can. How would I factor x squared minus 1? Right, I have x plus 1 and x minus 1. And because I have duplicated x minus 1, I also could write it as x minus 1 squared times x plus 1. Are we good so far? Okay? This is kind of where we left off last time in talking about multiplicities, right? We could actually set each of these equal to 0 now. So I have x minus 1 equals 0, which is x equal 1. With what multiplicity? What's my multiplicity? 2. Great. Because the exponent's 2. And on the other one, I have x plus 1 equal to 0, so that's giving me x equals negative 1. And what's that multiplicity? It's 1. And the reason the multiplicities are valuable, even though we didn't actually sort of reference them further that much last time, is because they tell me how the graph's going to look. They tell me whether I'm going to bounce off the graph or whether I'm going to cross, not bounce off the graph, excuse me, bounce off the x-axis or whether I'm going to cross through the x-axis. So I'm going to pause for a moment right here and plot these particular points on the x-axis because they will be part of my graph. And as we've referenced then, this x equal 1, which is the second value, what am I going to do? Am I going to bounce off or am I going to cut through at that point? Careful. It's multiplicity 2. Even? That's a bounce. So there's going to be a bounce right here. We just don't know if the bounce is above or if the bounce is below, right? Okay. And then this value x equals negative 1, which is listed over here as a multiplicity 1. Will I cut through or bounce off? That one will cut through. So I'll either cut through going up or I'll cut through going down. So let's look at the end behavior to make those decisions. So on my end behavior, I need to look at the degree. What is the degree of this polynomial?
3.
Right. I have a degree 3, which, just in case you weren't sure, is the number is odd, right? Yeah, it's an odd number. And the coefficient at the very front of this particular function, the original one given over here, is it positive or negative? My leading coefficient is positive. So I need an odd degree with a leading coefficient that's positive. Where am I on this chart? Odd degree puts me where? Top row, right? Odd degrees on the top row. In which case am I in? Positive or negative coefficient? Positive. So it's the first quadrant, right? It's this piece. This tells me that on the left-hand side, I'm going to be above the x-axis. And on the right-hand side, I'm going to be below the x-axis. Did I just say that backwards? I totally did. Oh my goodness. I'm going to blame it on the fact that you're sitting with the screen facing you and it's behind me. How's that? My left and right are just backwards. Okay, so it's going to go down on the left and up on the right. So we're going to go down on the left like this and up on the right like this. Those are the two pieces of information that are useful. One additional point that would be nice to plot would probably be the y-intercept. And it's also very easy to plot. If you want to find the y-intercept is simply the case when x equals 0. And if you plugged 0 into this equation, what would you get? 1, the number at the end, right? Because all the x's would go away. So if I plotted the point 0, 1, it would be right here. Agreed? Yeah. And I'm supposed to be cutting through the x-axis at negative 1. That's what we said. And I'm supposed to be bouncing off the x-axis at positive 1. Smoothly, so it connects something like this. Any questions on that? All right.